In our previous example of a linear system with three unknown variables, which was solved by elementary row operations, we actually reduced this system to this form, and this is known as reduced row echelon form. So in this case, we obtained a unique solution by inspection. Now in general, we have a row echelon form which has the following properties. So if a row does not consist entirely of zeros, the first non-zero number is a 1. So here is an example where we have the first number in each row being a 1. And here is another example, and another example here. So the first number is a 1, as we can see. And here is yet another example of this property. Now the second property of the row echelon form is that rows with all zeros are placed in the bottom of the matrix. So here, for example, we have all rows of zeros, and if we suppose this matrix was something like this, then the first rule of the row echelon form is satisfied, because the first non-zero numbers are 1 in the rows that don't consist entirely of zeros, and we also have the rows with all zeros being placed in the bottom of the matrix. And the next rule is two successive rows that don't consist entirely of zeros. The leading one in the higher row is further to the left compared to the lower row. So as we can see, the 1 in the higher row is further to the left than the 1 in the lower row. And the same applies to the third row compared to the second. So here we also see that as we go down the rows, the 1s are further to the right. So in addition to these three rules, which are the properties of row echelon form, we have an additional rule for the reduced row echelon form. So in addition to these three rules, the additional property for a reduced row echelon form is that each column that contains a leading 1 has zeros everywhere else in that column. So as we can see, we have all leading 1s in each row of this matrix, which have zeros everywhere else in each of their columns. So similarly in the second column and the third column. So this matrix here also has leading 1s in every row, and in the first column we have all zeros, but in the second column we don't have all zeros apart from this leading 1. So therefore this matrix here is only in row echelon form, not reduced row echelon form. And similarly for this matrix, we can see that every row has a leading 1, but for the column corresponding to this one, we have -3. So there's not all zeros in that column, and therefore this matrix is also in row echelon form, but not a reduced row echelon form. And another example is that this matrix is in reduced row echelon form, because it satisfies the properties of a row echelon form where we have a leading 1 in the first row, and the rows consisting of all zeros are placed in the bottom of the matrix, and in two successive rows with not all zeros, the leading one in the higher row is further to the left. So these rows consist entirely of zeros, so this rule is satisfied automatically. And then where we have a leading 1, we have zeros everywhere else in that column, which is the reduced row echelon property. So the row echelon form is a necessary condition for a matrix to be in reduced row echelon form, but not the other way around.